recorded.
Okay. So what we're going to do today is review some basic concepts of matter and energy. And then we are also going to start into units of measurement if we get that far. So I wanted to remind you that you have homework questions, chapter 2 and 3 review questions. It's all of the questions at the end of chapter 2, and it's questions 1 through 22 in chapter 3. They're due February the 1st, so you've got a while. Make sure that you write both the question and your answer so that you can use it to study. But I want to remind you of that. And today's material comes from chapters 2 and chapter 3, again, in the textbook. All right, so when we think about our environment, everything in nature can be classified as either matter or energy. And both of these are what we would call conserved quantities. And we'll talk more about that a little bit later. But these conserved quantities can change form, but they're always a constant amount. So we'll start with some definitions or defining matter. So anything that occupies space and has inertia is considered matter. So if you look around your workspace and you see your computer, and you see a calculator, you see a pencil, you see your water bottle, the physical things that you can see are easy examples of matter. They occupy space. Now, what does it mean to have inertia? We'll talk more about inertia when we get to the section on classical physics. But inertia is simply a tendency of a body to maintain its present position. So for example, if your calculator is sitting on your desk beside you, you can see it occupies space. Also, you can see that that calculator is not going to move on its own. It's not going to suddenly fly through the air. It's not going to jump off your desk and move. So matter is any object that occupies space and has inertia, meaning that its present state is not going to change unless it's acted upon by an outside force. So for example, if you reach over and you pick up your calculator, you've moved it. You have applied a force that changed its state of inertia, but it's not going to move on its own. Generally, when we think about matter, we think about the states of matter, how they exist. And matter exists in either solid, liquid, or gaseous states. So for example, it's always good to use water as an example, because water in its typical form is liquid. If we freeze water, it becomes a solid. If we heat water, it becomes a gas. So if we compare these different states of matter, we can say that solids have a definite shape and a definite volume. So for example, again, look at your calculator. It has a definite shape, a definite volume. It's not going to change. Liquids have an indefinite shape, but a definite volume, and they will conform to the container. So if you have a cup of water, you could pour it into different types of containers and it would have an indefinite shape. It would change with each container, but the volume would still be the same. And then gases have both indefinite shape and indefinite volume, because again, they will conform both shape and volume to a container. So these are the different states of matter. But again, by definition, matter is anything that has inertia and anything that occupies space. We've already alluded to this, but matter can change its state, and typically temperature is what alters the state of matter. So again, using water as our example, if water is frozen and we heat it, it converts from a solid to a liquid, or it melts. If we have water in a liquid state and we freeze it, it converts from a liquid to a solid. If we have condensation, water is converting from a gaseous state to a liquid state. If we have evaporation, we're heating water and it converts from a liquid to a gas. Each type of matter would go through these various states at different temperatures. I use water because an example, because it's common. It's a very common material. So at what point does water go from a liquid to a solid? What's its freezing point? What's the freezing point?
32 degrees. 32?
32 degrees. That's what we all pray for when we think it's going to rain, because if it's 32 degrees, hopefully we get snow. We might get freezing rain though, which we don't like. So at what temperature does water boil?
120?
212.
212?
212 degrees Fahrenheit, and this is on a Fahrenheit scale. The Celsius scale would be a little different. But again, there are, and that would be true for other types of matter. It would change states at variable temperatures specific to that particular type of matter. But again, matter exists as either a solid, a liquid, or a gas. And matter can change from one state to the other depending on temperature. And so here's an illustration. We see that we have a lake, so there's liquid, water is in its liquid state. The sun heats it, so it evaporates, it cools and condenses in the clouds and then rains. If it got cold enough, then it could freeze. So since temperature or heating can change states of matter, it's important to look at heat. And when we think of heat, I mean, we all know what heat is. You know, something's hot, it's warm. But heat, we've already said, affects the state of matter. So it's important to look a little bit more closely. So heat involves the flow of energy from one object or one atom or one molecule to another. And it has both kinetic energy and potential energy components. And we'll talk more about kinetic and potential energy a little bit later. But when we think about the temperature of an object, the temperature of an object is basically a measure of the kinetic energy of an object's molecules. So if an object has high kinetic energy of its molecules, then it will have a higher temperature. If it has lower kinetic energy in the molecules, then it will have a lower temperature. And again, the temperature can determine the state of matter, whether it's a solid, whether it's a liquid, whether it's a gas. Well, one thing that's important in radiology is heat transfer, how heat moves from one object to another. And this is important in our X-ray tube, because when we are producing X-rays in the X-ray tube, we are producing a tremendous amount of heat. And we need to remove that heat from the area of the anode so the anode doesn't melt. So it's important that we look briefly at these three methods of heat transfer. And it involves conduction, convection, and radiation. So heat transfer by conduction. And again, all of this is referred to as either heat transferred or thermal energy exchange, because that's what it is. We're transferring heat from one object to another. Now remember, temperature is a measure of kinetic energy at the molecular level. So keep that in the back of your mind as we talk about each of these different methods of heat transfer. And the first is conduction. Conduction is the transfer of heat by direct contact, or one object is touching another. If you have two objects touching, then direct molecular collision can occur as the molecules move. And heat will move from greater molecular motion to less molecular motion, or from hot to cold. If you think about cooking, and I don't know about y'all, but I'm not the world's best cook. As a matter of fact, I'm barely adequate, I guess, as a cook. But think about your pots and pans. You put the bottom of the pot on the stove. You turn on, I have a gas stove, so I turn on the gas. The gas flames heat the bottom of the pan. Well, the bottom of the pan is not the only thing that gets hot. The bottom of the pan gets hot, but also the heat moves throughout the molecules all over the pan, even to the handle. So if you have a pot with a metal handle and you're not careful and you grab hold of it without thinking, you'll get burned. Because even though the heat is only on the bottom of the pan, the heat source, heat spreads throughout by direct molecular collision. If you take a hot pan off the stove and you set it onto a surface, that surface will become hot because of that direct molecular collision. So again, heat transfer by conduction basically is when molecules are in contact, two things touch each other. Now, a second method of heat loss is by convection. And convection involves a mixing of fluids, and fluids are either liquids or gases. So in convection, hot fluids, say the hot fluids, if you think about a pan, the hot fluids are at the bottom of the pan because they're closest to the heat source. So those hot fluids will rise, carrying that thermal energy with them. They'll push the cold fluids down toward the heat source. The same thing occurs with gases or with air. If you have a space heater, the air around the space heater heats up and rises, pushing the cold air down. So it's like a flow of fluids. Again, hot rises, cold falls. Then we have heat transfer by radiation. And radiation involves a flow of electromagnetic energy. So as you are cooking, so you see this is a campfire and you see radiation showing, emerging from the fire. That is infrared or thermal radiation. It's produced by the heating. In the X-ray tube, our interactions that produce radiation produce infrared radiation. Our anode spins and casts it off as it spins. So a flow of electromagnetic radiation, either in the form of infrared or radiation or X radiation, is one way of heat transfer. When we think about our X-ray tube, a simple stationary anode X-ray tube transfers heat by conduction or direct contact. Our Coolidge tube, that we use that has a spinning anode primarily loses heat by radiation. It's casting it off as it's spinning. So heat transfer or thermal energy exchange, this is important to us because it affects our X-ray tube because of the great amount of heat that we produce in the X-ray tube. Now we're going to talk about the concept of mass. And notice that this mass is talking about how much matter is in a particular object. It's not mass that we set on our technique panel in our X-ray room. This is totally different. So we've already said that basically everything is composed of matter. Okay, anything that's occupying space, has inertia, is matter. Well, sometimes we need to know how much matter we have. And so we would call that the mass of an object. So the quantity of matter in an object is the object's mass. And when we measure it in grams, kilograms, those types of units. Now, one of the things that's important to differentiate is that mass is not the same as weight. We often confuse that. Mass is the quantity of matter in an object. Weight is the force of gravity on that object. So for example, the mass of an object never changes. Say I had a bar of metal and my bar of metal had a mass of 10 kilograms. on the Earth, its mass is 10 kilograms. If I put my 10 kilogram metal object in a spaceship and I send it to outer space, its mass is still 10 kilograms. If my spaceship lands on the moon and my metal object is moved to the surface of the moon, its mass is still 10 kilograms. The mass of an object is always constant. Weight, however, depends on the force of gravity. So on the Earth, my 10 kilogram object would have a certain weight dependent on the Earth's force of gravity. So we'll talk about that actually when we get to the classical physics unit. So weight on the Earth depends on the Earth's force of gravity. My 10 kilogram object in a spaceship in outer space where there is no gravity has no weight. So its weight's 0 in outer space because there's no force of gravity. When my spaceship lands on the moon and my 10 kilogram object is taken off of the ship onto the moon, it would have a certain weight dependent on the force of gravity on the moon. Just in general, the force of gravity on the moon is 6 times less than the Earth's force of gravity. So the mass of my object is the same wherever I am, on the Earth, in my spaceship, on the moon. The weight of my object is 6 times greater on the Earth than it is on the moon. And in outer space, my object has no weight. So again, that's the difference
On the moon. Is
mass and weight.
Right.
Mass is always constant, weight is variable due to the force of gravity, and weight is a force. So does that make sense? Make sense? I hope so. Okay. So we're going to switch gears a little, and now we're going to talk about energy because we're looking at some basic concepts of science. So energy is generically defined as the ability to do work. It can also be defined as the ability to cause a change in the motion or state of an object. So it can change an object's inertia. Units for energy are joules and ergs. And again, we'll come back to these a little bit later in our classical physics unit. But also in radiology, because our X-ray photons have such a small amount of energy, we can also measure energy in the unit of electron volts. So joules, ergs are typical energy units. For X-rays, we actually can measure energy in units of electron volts. There are lots of different kinds of energy. We have potential energy, we have kinetic energy. Potential energy is the ability to do work by virtue of position. So if we think about a bow and arrow where the bow is pulled back, ready to release, the bow has potential energy. If we think about a rock on the very edge of a cliff about to fall off the edge, that rock has potential energy. If we think about a rubber band pulled back, about to let go. It has potential energy. So potential energy, when you think of that, think of position. Energy by virtue of position. Then we have kinetic energy. And kinetic energy is the energy of motion. So anything that's moving has kinetic energy. For example, the skier skiing downhill has kinetic energy. A person riding their bicycle through the neighborhood has kinetic energy. An electron moving across our X-ray tube from cathode to anode has kinetic energy. Anything moving has kinetic energy because it's the energy of motion.
So could you say potential energy is stored energy?
It is stored energy. So yeah, and energy by virtue of position. So yes. All right, two other types of energy we're going to talk about generally. The first is chemical energy. And chemical energy is the energy that's released in chemical reactions. So we have in our body all sorts of chemical reactions occurring all the time that help us to produce the energy which is required of our bodies to work. A very common example of chemical energy that we all use all of the time are batteries. Batteries convert chemical energy to electrical energy. And so they are producing energy by virtue of the chemical reactions within the battery. So that's just a very common example of chemical energy. Electrical energy is something that we'll be dealing with throughout this semester, because one of the main things we're doing this semester is getting the background information necessary to understand our X-ray circuit and ultimately our X-ray tube, which is an electrical device. So electrical energy is just commonly called electricity. If we look closely at what's happening or what's producing electrical energy, it's the movement of an electron through an electric potential. And an electric potential simply is voltage. So if we apply a voltage to a conducting wire, it can cause electrons to flow, and that is electrical energy. Electrical energy is really a subclass of kinetic energy because electrons in motion, those electrons in motion have kinetic energy, but it's very specific, so we just consider it electrical energy or electricity. Thermal energy. Now, we've already talked a little bit about thermal energy. So when you think of thermal energy, we think of heat. Thermal energy, we've already said, is actually measuring the energy of motion at the molecular level. So it's kinetic energy at the molecular level, which makes thermal energy also a subclass of kinetic energy, because we're looking specifically at atomic and molecular motion. So then we have nuclear energy. And nuclear energy, by definition, is the energy contained in the nucleus of an atom. And the nucleus of an atom is a very minute structure, but there is a lot of energy contained within that nucleus if you can free it from the nucleus itself. So when we think about nuclear energy, there's lots of different things that may come to mind. You may think of atomic structure. You may think of Einstein's theory of relativity. You may think of nuclear reactors. You may think of all the different elements on the periodic table. You may think of atomic fusion. You may think of fission. All of these concepts can be thought of generally under the heading of nuclear energy because they're all interconnected. But for us, we're not going to really be dealing with nuclear energy this semester. So just know, in general, this is the energy that's contained within the nucleus of an atom. Now, the energy that we are going to be dealing with for this semester and all semesters with physics is electromagnetic energy. And we are primarily concerned with electromagnetic energy because that's what X-rays are. X-rays are electromagnetic. And there are many other types of electromagnetic energy. We've mentioned the electromagnetic spectrum, where you have X and gamma, you have all the different light waves, ultraviolet, visible, infrared, you have microwaves, you have radio waves. All of those are electromagnetic radiations. They all consist of two different fields, an electric field and a magnetic field that are perpendicular to each other, but they move through space together. And remember, the general term of the general definition of radiation is moving energy from one point to another. So electromagnetic energy can also be referred to as electromagnetic radiation. As I mentioned, there's lots of types. Here is the electromagnetic spectrum. At the low energy end, we have radio waves, then microwaves, then thermal or infrared, then all of the different visible lights, then ultraviolet, then X and gamma radiation. All of these are electromagnetic. They all travel at the speed of light. They all have the potential to do harm to the body, but in different ways. X and gamma radiation, which are at the high energy end, are ionizing. They have enough energy to eject electrons from atoms. Visible, ultraviolet, these light waves can't ionize you, but they can certainly give you a sunburn. Thermal can burn the skin, obviously. Microwaves can damage, and radio waves, I don't know that radio waves are really damaging. I certainly hope not, because they're all around us all the time. But they have some similar characteristics, but then obviously some different characteristics. But all of these are electromagnetic. They all consist of the electric field and the magnetic field perpendicular to each other, moving through space together. Now, one of the things that we mentioned initially is that matter and energy are conserved quantities. And what that means is that you can't create or destroy it, but you can change its form. So for example, we mentioned with a battery, chemical energy is converted to electrical energy. That's a transformation. Here we can have radiant energy converted to chemical energy. The sun makes the chemicals in plants, cause them to grow. We can use chemical to motion or to kinetic by automobiles using mechanical energy sources. If we have a space heater, we can convert electrical energy to thermal energy. So energy conversion goes on around us all of the time. But the important thing to remember is that energy is a conserved quantity, as is matter. In radiology, we use a special term called a transducer, or a special device called a transducer, specifically in ultrasound. There are many other transducers in the world, but that's the one that we use in radiology. Transducers are devices that convert energy from one form to another. An ultrasound probe converts electricity into sound waves. And then as sound waves strike it, it converts sound waves back to electricity. So it is a transducer. A light bulb converts electrical energy to electromagnetic energy in the form of visible light. So it too is a transducer. An X-ray tube converts electrical energy into electromagnetic energy. It's also a transducer. But in reality, when we think of our field of imaging, the only place we really use the term transducer is with sonography. So the ultrasound probe literally is called the transducer. But again, there are many, many different devices that convert energy from one form to another. So we said that energy was a conserved term or conserved concept, so is matter. So just like energy can't be created or destroyed, but only converted from one form to another, the same is true of matter. And so again, if we think about the example that we used earlier with water, you know, if we heat it, it becomes a gas. If we cool it, it can become ice. We can change its form, but we really don't change the amount of matter that we have. Einstein is a very famous physicist, came up with the concept of mass energy equivalence and developed his theory of relativity. And part of that theory of relativity is this mass energy equivalence statement or equation. And he says the energy is equal to the mass of an object times the speed of light squared. So a very small amount of matter, such as the nucleus of the atom, if accelerated to the speed of light squared, can be converted into energy, and a very, very large amount of energy, because the speed of light squared is a huge number. So a very small amount of matter, if converted to energy, would create a very large amount of energy. And that was Einstein's theory. So he basically, again, it's the theory of relativity. I'm not sure if we can accelerate things to the speed of light squared. I'm sure that we probably can. But we do see this mass energy equivalence occurring in some of our interactions with very high energy X-rays and matter. And you'll learn more about that in the summer semester when you have your safety class, because you'll talk about interactions between your X-ray beam and the patient's body. And in the therapeutic range, when we're dealing with very, very high energy photons, you get an interaction called pair production, where we get mass energy conversion. So anyway, that's Einstein and his equation that relates the two. And we really won't be working with this semester. We'll be focusing more on classical physics or Newtonian physics when we get to that section. So what we've done so far is to just review some basic concepts. And so before we go on, I just wanted to see if any of you have any questions about what we've already covered, what we've just covered. This is just some basic definitions and things. And this information is in chapter 2. A lot of what we've covered is in chapter 2. I was going to try to find the page numbers. Maybe from pages 20 to 27, so forth, something around those pages. So any questions? Any questions at this time before we go ahead? No? All right. So then we will continue on. And before we continue on, I want to tell you, we're going to do units of measure. So one of the handouts I gave you was a table that looks like this that says across the top measurement systems. So you might want to pull that out because we'll be filling it in as we go along. Okay, so now we are going to talk about units of measurement. And this is also in chapter 2, and it begins at the very beginning of chapter 2 on page 17 and goes through basically, I guess, pages 20. So not very many pages because these are some basic concepts. So when we are working problems, when we are doing experiments, we have to be able to quantify different measures. And in order to do that so that we can compare with the work of other scientists, we have to have standardization. And so over time, there have been standard units of measure developed. So we're going to define some quantities and then talk about unit conversion. So the first thing we're going to define is simply, what is a unit? Well, a unit is some quantity that is used to measure something. So for example, if I want to measure distance, there are a lot of different units that I can use to measure distance. I can measure distance in inches, in feet, in miles, in kilometers, in meters, in centimeters. I can measure distance in angstroms. So most of you have probably heard of all of those units except possibly angstroms, but all of those are standard units of length or distance. So a unit is just a quantity that's adopted as a standard of measurement. And we'll talk about different kinds of units as we go forward. Now, there are different measurement systems across the world. And if you have your chart, you'll see measurement systems across the top, and you see 4 different measurement systems. There's the British, the Systems International, the MKS, and the CGS measurement systems. So every measurement system has something that are referred to as the standard units. And the standard units are the basic units in any system of measurement. They can also be called fundamental units or base units. And basically, these are the building blocks for all of the other units in that system of measurement. And like I said, we're going to look at 4 different systems of measurement. So a standard unit is one of the basic units of the system. Then you have derived units. Well, the derived units are the units that are built from those basic units. They are more complex and they are derived by combining those base units in a variety of ways. Now that may not make sense now, it will make more sense when we start looking at some examples. And we'll get to that in just a few minutes. So like I said, there are 4 different systems of measurement. The first is the Systems International, which is the International System of Units. Then we have the MKS system, which MKS stands for meters, kilograms, and seconds. And these are the base units of that system. Then we have CGS, which is centimeters, grams, and seconds. And those are the base units for that system of measurement. And last, we have the British system. In the British system, the foot, the pound, and seconds are the base units for that system. In the International System of Units, or the SI units, and in the MKS and the CGS system, all of these are metric systems, okay? Most of the world is using metric systems and has for a long period of time. The United States was supposed to convert to the metric system in the mid-1980s and just never did. So in the United States, you will see some things measured in the British system, and then you will see other things measured in one of the metric systems, as long as you can differentiate what they are. But the Systems International and the MKS systems have the same 3 basic units. So in the Systems International, their basic units are also meters, kilogram, and seconds. So if we have basic units, we also have to have basic quantities, or the standard quantities. And the standard quantities are length, mass, and time. So length is pretty easy to understand. You know, it's a measure of distance. How far? Mass, we've already defined. Mass is the quantity of matter in an object. And then time is the period in which some action occurs or some condition exists. So for us, if we said we took an X-ray exposure that lasted 0.1 seconds, you know, our exposure existed for 0.1 seconds, so that's the time. So the standard quantities are length, mass, and time. Each system of units has a specific unit associated with each standard quantity. So if we think about the systems, if we look at our paper, we see the first is the British system. Well, the standard unit of length in the British system is the foot. The standard unit of mass is the pound, and the standard unit of time is the second. If we look at the MKS and SI systems, the standard unit of length is the meter, the unit of mass is the kilogram, and the unit of time is the second. In the CGS system, the unit of length is the centimeter, the unit of mass is the gram, and the unit of time is the second. the only unit consistent across all systems of measurement is the unit of time, which is in seconds. So whether you're in the British system or the MKS or the CGS or the SI system, the unit of time is always in seconds. So if we look at systems of units, on the bottom, the foundation of every system are the base quantities and the base units. So our three base quantities are length, mass, and time, and their associated units in the MKS system, which is the one that we'll work in most often, is meters, kilograms, and seconds. So those base quantities have associated base units. Derived units, these are more complicated concepts, and their units come from these base quantities and units. They're derived, and we'll do some work on that in just a moment so it'll make more sense. But some examples of derived units, we've already talked about energy, but there's power, work, momentum, force, velocity, acceleration. And we'll look at all of those concepts when we get to the unit on classical physics. And so as we go along, we'll be building our systems of units. And then within each system of units, there are also some special quantities. And the units of radiation are considered special quantities and special units. So as you go through the program, we'll talk about exposure, dose equivalent, activity of radioactive substances. All of those would fall into a special quantities category. And we're not going to worry about them in this class. You'll talk about those in radiation safety and in radiation biology, and also in QC. But anyway, we're going to focus on the base units and the derived units. And like I said, in the MKS system and in the Systems International system, these are the three fundamental quantities or base quantities and their associated unit. It's important to know what your base quantities are, as well as the derived quantities, because they are different in different systems, but when you're working problems, you have to work in the same system of units. So you couldn't express a distance or a length in meters and a mass in pounds and a time in hours and be able to work that problem. You have to convert to the same system of units. Okay? So it's really important. That's why we have the chart to sort of keep you in line. So the next question is, okay, so we have all these different systems of measurements. We have these standard quantities and these standard units. Who comes up with these things? Well, in reality, there is an International Bureau of Weights and Measures, and it's in France, and they are the group that sets the standards, and they are very serious. I said, these people need to get a life. I can't imagine anything more boring than this, but obviously it has to be done. So to give you some examples, in the MKS system, the standard unit of length is the meter. And a meter initially was defined as the distance between two engraved lines on this platinum iridium bar. So it was an arbitrary assignment. Here's this bar, there's a mark here, there's a mark here. That distance between the two, that's a meter. That was the original definition. Well, it has been refined over time to be more and more precise. In 1960, they changed it from the distance between those two marks to 1.65 times 10 to the 6 wavelengths of orange light emitted from Krypton 86. Now that's very specific. How they came up with that, I don't know. But then it's been refined even again. So the current definition of a meter is the distance traveled by light in 1/299,792,468 of a second. So obviously a very specific definition. If somebody asked me how far was a meter, well, I just hold my arms apart about this far, you know. But again, very technical, very specific definitions by the Standards Bureau. The same thing with the kilogram. The kilogram is the standard unit of mass in the MKS and the SI systems of measurement. The kilogram was defined as the mass of 1,000 cubic centimeters of water at 4 degrees Celsius. I'm not sure why 4 degrees. Why not 0? It's frozen at 0. But anyway, this was the standard. Then they developed an international prototype kilogram that is this platinum iridium cylinder. So again, very specific standards that are set by the International Bureau of Weights and Measures. The standard unit for time is the second. So this definition of the second has also changed, and this is the standard unit across all systems, okay? Because the second is the unit of time, whether it's British system, SI system, MKS, or CGS system. And initially the second was defined as 1/86,400th of a mean solar day. And they got that by saying, okay, every day has 24 hours, every hour has 60 minutes, every minute has 60 seconds, and if you multiply all that out and divide it into 1, it's 1/86,400. Now, they have even more precisely measured a second by basing it on the vibrations of cesium atoms in an atomic clock. And the picture here illustrates the first atomic clock that was built many, many years ago. So we laugh, or I laugh, because I think, you know, I don't know that I care that much about how precise the units are, but obviously somebody does. So the International Bureau of Weights and Measures refines these standard units, and over time they have changed. They have been more precisely defined. And you don't need to memorize any of these. This was just to give you an idea of the importance of this to the scientific community. What you need to know, basically, there are 4 different systems of units. Each of those systems of units has 3 fundamental quantities: length, mass, and time. And you need to know the fundamental unit associated with each of those fundamental quantities across systems. So since we've talked about the fundamental quantities, now we're going to look at some derived quantities and their associated units. And we're going to start with some of the basic ones: area, volume, density and velocity. Okay, so we'll start with area. And we know when we're talking about the area of a surface that it's calculated by either measuring the length times the width, if it is a square or a rectangular surface, or if it's a circular surface, area is equal pi times the radius squared. So when we think about units associated with the derived quantity of area, area is calculated by multiplying a length times a width. So that's two distances or two lengths. So if we multiply, say for the MKS and SI system, meters times meters, our unit becomes meters squared. If we're in the CGS system, we're multiplying centimeters times centimeters, so our unit for area is centimeters squared. And if we're in the British system, the standard unit of length is the foot, so the unit of area would be square feet. So again, when we think of area, it could be something like measuring the surface of your desk, measuring the surface of, or the area of your room, your home. That's the reason that when we think about if you're looking at buying a house or renting an apartment, whatever you're doing, one of the common questions is how many square feet? Well, that's telling you how much living area that you have. So the derived unit is area, which is a measure of a surface, and the units are in distance squared. So meters squared, centimeters squared, or square feet. So that's the first derived unit. The next derived unit is volume. And when you're talking about volume, you're talking about how much will a container hold? What's the capacity of a container? So now we're looking at 3 dimensions. To calculate the volume, we not only have to know the area, but we also have to know the height. So volume is length times width times the height, or if it is a cylinder, pi times the radius squared times the height. Ultimately, what you're multiplying are 3 units of length. So your units are basically distance cubed. So if it's MKS and SI, it's cubic meters. If it's CGS, it's cubic centimeters. And if it's British, it's cubic feet. Because you're looking 3-dimensionally at a container and how much it will hold. Okay, so the next derived unit is density. And here we're talking about the density of an object. For example, if you think about air has a low density. Gases typically have low densities, but you would think of the density of, say, lead as having a high density. By definition, density is the mass per unit volume. So how much matter have we crammed into a certain container, into a certain volume? The formula for density is mass divided by the volume. So the units would be units of mass divided by units of volume. So if we are in the MKS or the SI system, our unit of mass is the kilogram and our unit of volume is cubic meters. So in those systems, the unit for density is kilograms per cubic meters. In the CGS system, it would be gram per cubic centimeters. And if it were the British system, it would be pound per cubic foot. Because by definition, density is mass per unit volume. And so your units must parallel the concept. And the last of the derived units that we're going to look at is velocity. And velocity, when you think of velocity, I think of speed. How fast are we going? A more technical definition of velocity is that velocity is the change of an object's position with time. So for example, if I'm driving my car at 50 miles per hour, in 1 hour's time, I will be 50 miles away from where I am right now. So velocity, the formula for velocity is that velocity is equal to distance divided by time. So your units will be units of length or distance over units of time. So in the MKS and the SI systems, our unit of length is the meter, our unit of time is the second. So velocity is quantified in meters per second. In the CGS system, it's centimeters per second. And in the British system, it would be feet per second. So these are just some examples of some derived units. And again, when you think about a system of measurement, the fundamental units or the fundamental quantities are length, mass, and time. The fundamental units are associated with each of those quantities. For MKS, it's meter, kilogram, and seconds. The derived units are more complex because those derived quantities are more complex. So the derived units are combinations of the base units in any system of measurement. So some things to remember. First, every measurement has two parts. It has a magnitude and it has a unit. Without a unit, the magnitude makes no difference, makes no sense. You can't interpret it. For example, if I said, or if I ask you a question and I said, how far do you live from main campus? And you told me 5. Okay, 5 what? Do you live 5 minutes from campus? Do you live 5 miles from campus? Do you live 5 kilometers from campus? Do you live 5 days from campus? You know, if you have no unit, the magnitude is meaningless because I can't interpret your answer. So for every problem that we work in classical physics, there will be both a magnitude and a unit. In basic math practice, we don't deal with units, but in the classical physics section, we will. So you must have both a magnitude and a unit. Also, you have to work within the same system of units. You can't have part of your concepts in the British system and the other part in the MKS system and get an appropriate answer. You have to convert. You could convert all quantities to the British system and work the problem, or you could convert all quantities to the MKS system and work the problem. But you cannot work the problem if half the quantities are in one system and half are in the other. Because we have to convert, we have to be able to understand conversion problems, unit conversion, and we also have to understand the prefixes used in the metric system. So on page 20 in your textbook, there's a table that has common prefixes that we will be using. And these are the 6 most common. Giga, mega, kilo, centi, milli, micro. Giga, symbolized by the capital G, is 10 to the 9th. So it's hundreds, thousands, millions. Giga is 1 billion. Mega is 10 to the 6th. So it's 1 million. Kilos, 10 to the 3rd. It's 1,000. Remember, positive exponents are large. So if you had 1 gigabyte of data, that means you've got 1 billion bytes of data. If you only had 1 megabyte, you'd only have 1 million. So again, these are large, these prefixes are associated with a large quantity. Then we have centi, milli, and micro. Centi means 1/100th, or it's 10 to the -2. Milli, 1/1000th, 10 to the -3. Micro, 1/1,000,000th, or 10 to the -6. So we will be working problems using these prefixes and unit conversions. So the first thing you need to do, if you haven't already in the past, I'm sure that many of you have, is you have to memorize these prefixes because you have to know them. We'll also be dealing with common conversions between systems. So between the British system and the metric systems. So here are some common conversions that we'll be using with our unit conversions. And you don't have to memorize all of these, but you'll remember them as we practice. And the next class, what we'll be doing predominantly is working unit conversions. So, any questions? Any questions about what we've covered today? If not, what I want you to do for the next class is make sure you have read the section in the chapter, which is chapter 2, basically from pages, I want to say 17 through the entire chapter. So make sure you've read chapter 2. Don't forget the study questions at the end of chapter 2 are homework. And